So last time we were talking about this idea of random variables and how random variable is not really a variable, nor is it random, but it's some phenomenon. And I can make observations of it, and I can store the observations in a list, and then looking at a list of numbers is kind of annoying, so it's a little nicer to look at a distribution. And the big question I had here was, okay, I've got two random variables, two phenomena. The two squirrels in my backyard burying nuts, two evolutionary algorithm configurations, something, and I want to make a comparison. And what's neat about thinking about stuff this way is it allows us to make interesting conclusions. And it actually allows us to ask really whatever question we want and then look to answer it. So here, I'm looking at these two things and I want to know, are they producing different output really? We often like to start with the null hypothesis, which is no, assume they're not. But more on that in a moment. I look at these two distributions, I plot them against each other, and the first thing I want to do is just the eyeball test. Do they look different? And when I look at it, I mean, we saw last time when I said, do they look different? We kind of got a humming and hawing of people going like, yeah, to like, well, I don't know, maybe. Superficially, I look at this and I say, yeah, they look different. But once I consider that I only have 50 observations of each, and maybe it just so happened that, like if I were to take 100 observations of each, how would, like if there were 100 data points instead of 50, if there are 100 data points in here and plotted them against each other, how different would they look, right? Like I don't really know how different they are. When visually analyzing, they do appear to be different, but the data is noisy. A range of values are obtained from each. And there's only 50 observations of each. So it's really difficult to actually say. They may be effectively the same, or maybe not. The two groups do not take different amounts of time to recover from the flu. For example, the squirrel I named Jimbo does not bury more nuts than the squirrel I named Sir Laura. And there really isn't more blonde people this year versus last year walking past the building between 10 and 11 a.m. So that's kind of, this is how the question we're asking. How many nuts did squirrel A bury versus squirrel B? Are they really different, or is it basically the same? Any questions so far? Because this foundational understanding of what I'm talking about, if it didn't make sense, there's no sense of me carrying on. So let me know if there's any follow-up questions of this. All right. Now, let's talk through an example here. This is an arbitrary example, but I'm using this example because this is like the classic example that everyone uses. Consider a drug trial. I'm a big pharmaceutical company, and I'm inventing a new drug. A group of 50 people given a new drug that is intended to reduce the recovery time of the flu. Another group is given a placebo. For those of you that don't know, a placebo is like a sugar pill. It's a pill where or it doesn't need to be a pill, but it could be a treatment where you pretend to give it to somebody, but you're not really giving them anything. So usually in a drug trial like this, it's a randomized drug trial where what you do is you have the two people, but the patients don't know if they did or did not get the drug. You tell them they did. And the people administering the drug also don't know. They just administer either a placebo or the actual drug. And the idea is, for those, like I designed the experiment, I know who got the actual drug and who got the placebo, but no one else does. So they all go do their thing. And at the end, I want to watch the recovery times. And I know who had the placebo and who didn't, or who had the real drug and who had the placebo. So that's the situation. No one in either group knows that they have the new drug or the placebo. So here, The random variables are the two groups. There's two random variables, one for each group. The group that got the placebo and the group that got the actual new drug. And the observations I'm going to make are the recovery times from the flu. The recovery time, now, you know, when you're playing a game like this, the recovery time is itself also a random variable, but let's not get too hard into that right now. So here is my plot. It's actually the same distributions as the one before, right? The drug group and the placebo group. I want my drug that I've invested $1 billion into to reduce flu recovery times. And when I'm looking at this, I go, see, the orange distribution definitely looks like it reduced the recovery time. That's good. But did it really? The placebo group, I measured all their recovery times, and that's their distribution. The drug group, I measured all the recovery times, and that's their distribution. So far, so good. Any questions? All right. With the above example, the average recovery time of the placebo group was 15.4 days, and the average recovery time of the drug group was roughly 13.8 days. These are the averages. The drug group recovered, on average, 1.6 days faster. All right, let's pretend maybe this drug didn't cost $1 billion maybe it only cost us $1,000. And we go like, hey, 1.6 days isn't so bad for $1,000, right? I'm not costing how much it costs to make the drug. I mean how much it costs to invent the new drug. If I spent billions of dollars for 1.6 days, I'd probably be pissed. But anyways, these are just summary statistics. Averages, first of all, an average is only really helpful if your data is normally distributed, which if you look at our distributions, they're fine distributions. I'm happy with them. But it's just a summary statistic. A summary statistic that tells you, well, on average, where is it? It doesn't really tell you anything about how wide the distribution is, how narrow the distribution is, how lopsided the distribution is. No, it's a single value that is being used to summarize that distribution. But when you look at that distribution, there's a lot going on. A simple single summary statistic doesn't really cut it. It's tempting, but it doesn't tell us much about the actual distributions of what's actually going on here. So comparing just the means is not great. You might be tempted to conclude that it clearly works based on the averages, but really all I can say from those averages is, on average, one group recovered that much faster than the other. But that's really not a big conclusion. When observing the distribution, it's clear there's more nuance. Additionally, there were only 50 observations from each group. Every individual is different, and every observation is different, right? The drug might be effective, but if I gave it to you, and I gave it to myself, it might have wildly different effects, right? And if I were to do this again, if I were to redo this trial, chances are the distributions are going to look a little different. Maybe not wildly different, but they're going to look a little different. So what are the odds? The big question I have is, okay, let me say that point again. If I were to do this again, if I were to do this exact same trial again, with more people even, the distributions I get would look a little different. Because everyone's different. Do you agree? That's what's going to happen. So really what I want to know is, listen carefully. What are the odds that this just happened by chance? What are the odds that the drug group recovered 1.6 days faster on average by chance? What are the odds of that, okay? Because right now, this is just one trial, and I got 1.16. But if I were to do it again, would I get 1.16? If I were to do it another time, would I get 1.16? A little better, a little worse? I don't know. But the point is, I could keep doing this over and over and over again. And I could look at what's the distribution of average recovery time differences. I can generate another distribution of the differences in recovery times. So far, so good? So this is where we start with the null hypothesis. Always start assuming there's no difference. You don't have to start by assuming there's no difference. You could go about this assuming there is a difference and still make the same conclusions, but I find it a little easier, and I think people just in general find it a little easier to follow this chain of reasoning from the null hypothesis. And if you get confused, slow down and listen carefully to what I'm saying. When I say null hypothesis, it may sound like it's an arbitrary position to take, but it makes these assumptions a little easier. With that assumption, it makes the following argument a little easier. We start by assuming the null hypothesis. So we assume the drug, listen carefully, we assume the drug has no actual impact. The assumption is, at the end of the day, sure I made all those measurements, but at the end of the day, we're assuming the drug had no impact at all. It really didn't have an impact. All right? So if the drug had no impact, then it could be expected that the average recovery time would be no different than the placebo. If it had no effect, the recovery times for the placebo and the drug group really should have no difference at all. Okay? That's a safe conclusion to make. We should assume there's no difference. And if there is no difference, we should assume to see no difference in the recovery time, because that's kind of what we're measuring here. If both groups had the placebo, okay, it really wouldn't matter which person was assigned to which group. Would you agree? Let me say that again slowly. I'm saying I've got two groups, and I'm saying the recovery time of one group and the other group really should be no different. They should be the same. And if they are the same, it means, look, there were 50 people assigned over here and 50 people assigned over here. If it did, and I can't stress enough, I want you to pay attention to this, because students, I find this so simply intuitive and easy to understand, and students always get confused, and I think it's just because they're not paying attention. So pay attention. There's no difference between the groups. There were 50 people over here, 50 people over here, but the thing I did to them, this one got a placebo, this one got the drug, or vice versa, it doesn't matter. If there's no difference, I could have taken 25 of these people and actually put them over here, and 25 of these people put them over here, and I would have seen no difference, right? If it has no effect, if which group they went to didn't matter, then it wouldn't matter which group they were in terms of the recovery times, right? It should be possible then, if there is no difference, right? We're starting from the null hypothesis, we're assuming there's no difference. If there's no difference, then I could redo this whole experiment again in 2 seconds by just saying, no, that person and their corresponding recovery time that was in this group, pretend they were in that group. Basically, you take each person and their corresponding recovery time, shuffle them, and split them into 50-50. I don't care what group they were originally in. It doesn't matter. I'm going to save that for later. Again, there's no difference between the groups, right? The null hypothesis. So I just shuffle them and arbitrarily shuffle them. I could, if I wanted, I could generate every single possible combination of groups of 50 out of 100 people. Okay? How many is that? I think I might have it in here. There's a lot. I could generate every possible combination of, hypothetically, this is the placebo group, and this is the drug group. Shuffle them again, placebo, drug. Shuffle again, placebo, drug. And I can take the distributions of those, and I can compare them. I can compare their average differences. So yeah, it would be possible to assign each individual and their corresponding recovery time to one of the two groups randomly. if it didn't matter which group they were in, I could pretend they were in either group and it should have no impact on the actual results. Therefore, the difference in the average recovery time between the two randomly assigned groups would be an example of what one would get by dumb luck. When we start with the null hypothesis, we're saying there's no difference. That's like saying, look, there was a 1.6 day faster recovery time with the drug group. But we're assuming there's no difference. And if there is no difference, then that would mean that that 1.6 that we observed was dumb luck. Right? So I'm going to say, what do I have here? Can't remember. Was this the good one? Not bad. I'm going to remember my first thing, 1.6, was the average recovery time difference. But I'm assuming that's dumb luck because it shouldn't have mattered which group they were in. So I take the people, I shuffle them, look at their new distributions. Their measurements don't change. Each person, their recovery time goes with them to the group that they go to. And then after they're assigned 50 people, I measure their difference again. Another dumb luck observation. And this time I measure it, and maybe the recovery time difference was like 0.7. But, you know, this was the real observation, the one I actually made, but we're assuming it doesn't matter. So I randomly assign them, get the distribution, calculate their averages, what's their average difference. I do it again. I'm going to do this for every possible permutation of 50 people to each group out of 100. So shuffling the groups once and calculating the difference between the group averages will give one example of a chance difference. So that's another chance difference. I'll shuffle them again. Now I've got two groups of 50 people and their corresponding recovery times. What's the difference in their groups? All right, this time it was like -0.2. I do it again. This time their difference is -1. I do it again. This time their difference is -0.1. I do it again. 2. I do it again. 1.5. I keep doing this. I keep randomly assigning the people to each group, regardless of if they actually had the placebo or not, but I pretend, okay, you had the placebo, but let's pretend you got the drug, because it doesn't matter. It shouldn't matter if you had the drug or not. So it's possible to generate all possible combinations of 100 people into two groups. If all possible combinations are generated, all possible average by chance differences can be found. Now, in this particular example, there is 1.01 times 10 to the 29 combinations of splitting 100 people into two groups. Okay, there's a lot. So this is called the permutation test. Do every single possible one. There is an alternative called a randomization test where you go, well, that's a lot. So instead of doing it times 10 to the 29 times, just do it like a lot and be like, okay, that's probably sufficient. So here I did it with 1 million. I did 1 million different possible randomly assigning some here, some there. Do it again. Some here, some there, average recovery time difference. Shuffle again. I did that 1 million times. And after I did it, this is the distribution I got. All right? This distribution is the average difference in recovery times between the two groups. That's what this is the distribution of. It is not average recovery time. It is not the recovery time of individuals. It is the average, the difference between, I'm getting tongue-tied here, the difference between the average recovery times between the two groups. So this distribution is, remember, assuming the null hypothesis, there's no difference of having a drug or not. And if there's no difference of having a drug or not, then it doesn't matter which person went to which group. We're assuming that the recovery time had nothing to do with the actual drug. So by splitting the 100 people into two groups of 50 a million times, we have generated a million observations of what you would expect the difference in the average recovery times of the two groups to be by dumb luck. This is our dumb luck distribution. It doesn't matter what the recovery times are. Out of a million, it looked like 175,000 were basically, I don't know, how many bins between 0 and 1 do we have? It looks like we've got like 1, 2, 3, 4. So 2.5, 2.5. It looks like there's 170, well really, it looks like there's close to, what would that be? 2, 3.5, no, yeah, 3.5. 350,000 of them had a difference between like negative 0.25 days and positive 0.25 days. That's a lot. But we didn't actually observe, like we actually have our actual real observation, right? Our real observation was 1.6 days faster. Now, be aware that the sign all depends on how you calculated the difference, right? Am I saying did one go faster or did one go slower? It all depends on the directionality. So the sign's somewhat arbitrary. It just depends on how you asked the question. I'm seeing a lot of blank faces, so I don't know if it's because this is so painfully obvious or if it's because you're confused and you got stuck somewhere along the way. I'm asking you a question. Okay.
Don't you think, so you had your graph of differences, wouldn't that make more sense to just take the absolute value? Like the lower one.
This one, if I were to do the absolute difference? Well, then what's tough is it's possible, so you got to remember, it's possible that the drug had a negative effect, right? If I were to say, oh, the drug let me recover 1.6 days faster, that's like negative 1.6 days. But it's possible that, like, if I were to do the absolute value, what if it actually made me take 1.6 days longer to recover? So that sign matters. And there is some nuance to the sign and how we actually calculate the p-value that I'm going to skip. But it won't matter for the intuition. When I did this, I was plotting the recovery times of the two groups, but I'm saying it doesn't matter. And the average difference in the recovery time of these distributions was 1.6. 1.6, or I'm guessing it's negative 1.6, is one data point in this histogram. That was what I actually observed, but we assumed it wouldn't have mattered. We assumed that the recovery time didn't matter. If the recovery time, we assumed that the drug had no impact on the recovery time, meaning it was just dumb luck to get 1.6. So if it is dumb luck, then it wouldn't have mattered who actually got the drug or not. So let's pretend someone over here that didn't get the drug actually got the drug and do it again. What if these three people, and we flip them, do it again? Because it shouldn't matter. We're assuming it doesn't matter. So if it doesn't matter, this is the dumb luck distribution. Remember, this distribution is of something entirely different than the previous two. The previous two were distributions of the recovery times. This is a distribution of the difference in recovery times between two groups with arbitrarily assigned groups, a million times. So this is where the magic comes in. I wanted to know, what are the odds of 1.6 happening by chance? That's the ultimate thing we had. If I scroll up to the top, that's the question I ask. What are the odds that this just happened by chance? So let's find out. I observed 1.6. I have a million observations of, here's the dumb luck distribution. So what are the odds that I had a recovery time of 1.6 by dumb luck? Well, here's negative 1.6, because it made us recover 1.6 days faster. There's the line. The data point of 1.6 was here. So in order for me to know what are the odds of observing 1.6 or less, that's a very simple calculation to do. I have a million data points on this plot. There's a million. What proportion of the 1 million had a recovery time of 1.6 days faster or better? Basically, how many are here? There were 205. There were 205 of the 1 million, 205 of those dumb luck differences were better than what we actually observed originally. Meaning, there is a 205 in a million, or 0.0205% chance, roughly 1 in 50,000. There's a 1 in 50,000 chance that the drug got me an average recovery time of 1.6 by chance. It improved the recovery time by chance. We have the dumb luck distribution. We have a real observation. So what are the odds that a real observation happened by dumb luck? Well, what proportion was just as good, if not better, than what we actually observed? 105 out of a million. Great. This is the p-value. This is what a p-value is. When you do your t-test, when you do your Mann-Whitney U-test, this is what the p-value is telling you. Is what are the odds that you observe this by chance? There was a 0.205% chance that this happened by dumb luck. That's what a p-value is. Those distributions are different. The conclusion is, yes, there absolutely was a difference between them. At least there's a 49,999 out of 50,000 chance that there's a difference. But there almost certainly is a difference. There's a 0.0205% chance that our observation was dumb luck. So there was likely an actual difference. The drug actually had an impact on the recovery times.
So where do you get the 205?
Well, it was the two, well that was, I literally counted. So I went, there were a million data points here. I literally counted how many were less than or equal to negative 1.6 days. And this is how many there were. So I counted them, there were 205. So 205 out of the million is how many of the dumb luck ones are better than that. So there is a 0.02% chance that what I observed actually happened by chance. So this is what your p-values mean. when you're doing a t-test is an easy way to approximate doing like a permutation. This is what you really want to do. If you want to compare distributions, this is what you want. You don't want to do a t-test. A t-test is what you do when you don't have the time to do a permutation test. Because you know what, here's the thing, doing a permutation test is really easy if you have a computer. Doing a randomization test, which is like the simpler version, which is, okay, I'm not going to generate all times 10 to the 29 possible combinations here. I'm just going to do it a million times, randomly shuffle and hope for the best. A million is a hell of a lot less than times 10 to the 29. It was trivial for me to do with the computer. I'd just say shuffle, do it again, shuffle, do it again. I threw it into a loop. Now, if it's 1905, and I'm trying to do things by hand with pencil and paper, I ain't doing a permutation test or a randomization test, am I? I can't. I can, but it's not feasible. If I have a team of people working with me, maybe I'll do it in like a couple of months, I can get it done. So there are these quick and dirty ways to get a p-value that makes some assumptions and whatnot, like a t-test. There's nothing wrong with a t-test. Yeah, with the t-test you can get a p-value like that. You plug it into a closed form expression, bingo, bango, you got it. But this is actually what you want to do. The t-test is what we do when we go like, ugh, I don't want to do all possible combinations, right? But at the end of the day, this is what a p-value is. And hopefully, I think it's pretty damn clear, hopefully the intuition is really clear on what the p-value means and why it means what it means and why the null hypothesis is an important starting point. If it didn't matter which group they were in, it means that the difference in the recovery time I've just observed shouldn't have been impacted by the drug or not. Meaning it wouldn't have mattered if the person had the drug or not. So by assuming there's no difference, just pretend everyone was assigned to every possible combination of group, observe the difference, and that's the dumb luck distribution. And then what did you actually observe? Well, how many from the dumb luck distribution were just as good, if not better, than what you observed, and that's your p-value. What's the odds that you observed this by chance? Well, the odds are how many of those by chance were that or better. Any questions about that? Yeah.
So not really like the test itself, but more like specifically. So like say you're doing the test, you've got like crossover method 1 and crossover method 2. Like you do the test, you conclude crossover method 1 is better than 2, great. But like the problem is if you can't just conclude the crossover method 1 is better than 2, the problem is that crossover 1 is better than 2 given like every single parameter choice that you made, and you have like no assurance that it will generalize if you change like a single other parameter. So like, how do you like get any sort of assurance?
Well, that's the combinatorial explosion, right? Where every new like degree of freedom you add, the more combinations of things you need to go and test. Now that's not a limitation with this permutation, that's a limitation on how you're going to do the statistics. And that right there is a problem that everyone's been scratching their head with since the beginning of time. When you have these very dependent parameters that affect one another, how can you tease any of that out? And that's not easy. And a lot of times what you'll do is if you go in with good faith, maybe what you would do, if I wanted to show crossover 1 was better than crossover 2, I would run it on a suite of different instances of the same problem, a suite of different problems, and maybe a suite of different parameter settings. And I would do a series of these tests to be like, look, and in all these different various cases, like overwhelmingly. Now, you could then start to do like a meta-analysis where you're doing a permutation of the results of your permutation test, which you absolutely could do. But then, you know, combinatorial explosion, once again, how deep do you go? So there's no real answer. There's no real, like, here's what you do in that situation, because all you're pointing out is like, isn't it shitty when? Yes, it is. It is shitty. And that's why you try to control for all the variables you can. You try your best in good faith. You try to keep things consistent. But at the end of the day, if you studied one problem on one like reasonable parameter configuration and you just switched out the crossover, you can still make the conclusion that with all these settings, the way they are on this particular problem, this crossover performed better than that crossover. And everyone would know that, yeah, that is the most power you can make from that conclusion. But empirical evidence is better than no empirical evidence. So at least you have a data point to be like, look, it was better here. And if someone said, would it be better if you changed the problem? The answer is, I don't know yet. But that's interesting. Go try it. But of course, you don't do it. You just tell them to try it. That's the trick. When you go to a conference and someone says, why didn't you do it this way? And you go, instead of explaining, see, that's the problem. When you go to a conference and someone asks you, let's say you did that, and you're at a conference explaining why your crossover's better, and some asshole in the room says, well, why didn't blah, 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 blah. And of course, you've spent maybe 2 years thinking of this problem, and that person spent the last 20 minutes half paying attention to your presentation, and what they want to do is look smart in the room. So instead of explaining to them how dumb they are, what I usually say is, wow, what a great idea. That's a fascinating idea. You know what? Here, do it. And of course, they don't want to do it because they don't care. And that's a good way to shut them up. That's usually my trick. It's a good tip. Any other questions? So this is what comparing distributions means. And it's intuitive, which is great. If you want to start doing your permutation tests for your assignments, absolutely, sure, go for it. There's nothing stopping you. They're like in scipy.stats, there is a built-in permutation. It'll do it for you. It's hilariously easy to do. It requires a little bit more work than just doing like a Mann-Whitney U or a t-test, just because you have to give it like the statistic you're trying to actually compare. I would encourage you to do the permutation test or randomization test. In fact, let's go have a quick look here. There we go, look at that. I think it's got some examples below. Yeah, so there is, oh, look at that. It's even a nice distribution. So you can do it. There's a built-in function to do it in scipy.stats, but it does require just like one more step than doing just like a Mann-Whitney U test or a t-test. Here's my quick and dirty advice to you. If you wanted to know the easiest, best option, I would say do a Mann-Whitney U test. It's a little nicer than a t-test because it makes less assumptions about the data, so it's a little bit safer. Chances are the difference in the p-values you get will be minimal. But if you're looking to do one quick and dirty, do the Mann-Whitney U test. Don't really do the t-test, but everyone knows the t-test, so I'm going to mention it. Do a Mann-Whitney U. Again, I'm speaking in generalities and like, okay, quick and dirty. If you can, do the permutation test. It's definitely a lot more interesting. It's definitely the most powerful one, the most impactful in terms of like the conclusions you can actually make and the types of questions you could ask. But yeah, if you're working on one of the assignments or your project and you're like, let's do a permutation test. Yes, do it. Awesome. I encourage you. If you're like, F that, I'll just do the one line of code for Mann-Whitney U. Fine. Any other questions about that? All right, no sense starting a new topic right now. We'll end it here, I guess. Cool. All right, I'll see y'all later.